Hello, and welcome to Module 18, Lesson 1, which is Early Earth. So if we look at review term here, metamorphism is just when a rock undergoes change. So heat and pressure causes it to change. The more heat and pressure, the more change. So if we take this rock shale and it undergoes heat and pressure slightly, then it forms slate. If it undergoes more heat and pressure, then phyllite, schist, and gneiss. So we can see kind of where these would form. Different formations depend on temperature and pressure.
$4.6 billion years ago, an enormous cloud of gas and dust, called a solar nebula, swirls in the Milky Way galaxy. A new solar system is born, our solar system. In a process known as the conservation of angular momentum, gravity collapses the cloud, turning it into a flattened, spinning disk. The powerful gravity pulls most of the gas into the center of the disk, and this gas gradually condenses, coalesces, and ultimately forms our sun. Leftover gas and dust swirls around and slowly begins clumping together. Now the strong solar winds blast outward from the sun, blowing lighter materials like hydrogen and helium far out. Heavier material like dust and rocks resist the solar wind and remain close to the center. And it's this heavy material that begins clumping together, eventually forming the prototypes of the inner rocky planets, including planet Earth. It's the Earth's dense, rocky core that forms first. Heavy materials like iron and nickel gravitate to the center, whereas lighter materials drift to the outside, eventually forming the Earth's crust. Over millions of years, the new Earth begins trapping stray gas in its powerful gravity, and this gas eventually becomes our sacred, life-saving atmosphere. But suddenly, around 1 billion years after the Earth is formed, Theia, a large Mars-sized body, floating freely in the new solar system, crashes into Earth, causing near catastrophic damage. Millions of pieces of the infant planet blast outward into space. And some pieces become trapped in the Earth's gravity, ultimately becoming our moon. Today, comets are rare in the inner solar system, only appearing a few times every several decades. But during the early primordial times, comets were very abundant throughout the entire solar system. It's believed these icy comets colliding with a young Earth were the initial cause of water on our planet's surface. Of course, since then, Earth has become the pleasant, life-bearing planet we know as home. We enjoy an abundance of vegetation, water, tools, and technologies. We live a safe and protected life under our atmosphere. That is, until the sun turns into a red giant, incinerates the entire planet, and wipes out all evidence that Earth ever existed. But not to worry, we've got 5 billion years to figure that out, and we can discuss this in another episode. It takes weeks to make videos like this for you to enjoy. Do us a favor, comment, share, and subscribe below.
All right, so kind of a recap on what we have talked about, especially with the timeline that we did last week. So basically, the age of the Earth, it formed 4.6 billion years ago, and it formed with the rest of the solar system. So when it first formed, it was very hot, volcanically active. There's no continents that existed because there was no water, and so it was just kind of a solid mass. And then we call this eon the Hadean. And so this is when Earth was basically forming. There's no life or anything like that. And this is well beyond or well before anything ever existed, even cells or anything like that. So that was about the first 600 million years. All right, so if we kind of look at this timeline here, we can see the Archean is is when we first started to see life forming. So that's the eon where life first began. The Hadean is this first 600 million years where it was basically just formation of the Earth. So like you guys did with the timeline, you had the earliest evidence of life, which were cyanobacteria and algae. And then we have an abundance of unicellular organisms, kind of like the foraminifera and the protozoa that we looked at on one of the rocks. And then other things form, some eukaryotes, prokaryotes, and then more advanced life afterwards. All right, so when we look at the Earth's crust, the oldest rocks that we can find are 4.28 billion years in age. So not quite 4.6. But we know that the solar system formed all at the same time. And when we look at rocks from different planets, well, not planets, but the moon, for example, we have looked at some rocks from Mars. But when we look at rocks from meteorites, we can also see that those are all 4.6 billion years old. And so with Earth, it's a little bit unique because we have plate tectonics going on and the rock cycle constantly renewing rocks. It's harder to find older rocks. But our oldest rock that we can find is zircon. So zircon is pictured here, and it survives erosion and metamorphism. So it doesn't metamorphosize even under a lot of intense heat and pressure. So these are the oldest rocks that we can date that are about 4.2 billion years old. All right, so we use radiometric dating to figure that out, and we can see that zircon is approximately 4.4 billion years old. So the Earth is at least this old. But when we look at the meteorites and look at other things, we can see that it's all roughly points to about 4.6 billion years old. It could be older, but that's the age that we think so far. Could be older, though. It's not younger. So when we look at these meteorites that I mentioned, those are basically just shooting stars or rock that has fallen from the solar system. And we can see that those are about 4.5 to 4.7 billion years old. And the solar system formed at the same time. So if these formed, and they're part of our solar system, formed, and they were 4.7 billion years old, then our solar system has to be approximately 4.7 billion years old. Excuse me. All right, so when we look at the moon, I mentioned that the moon has rocks that are around 4.4 to 4.5 billion years old. So the moon formed from, like you saw in the picture, probably a large body, a protoplanet or something hitting the Earth early on. And so that is the same age. It was forming at the same time. So since that is approximately 4.5 billion years old, then the Earth has to be at least 4.5 billion years old. All right, so heat sources for the Earth. So the Earth does have heat internally, and that comes from the core. And so there's a combination of things. So gravitational contraction. So as gravity pulls things together, it creates more pressure, which creates more heat. Radioactivity. So those are things like uranium breaking down, and that gives off heat. Asteroids, meteorites, things that hit the Earth, those create heat as well. And so those are different ways that Earth's heat sources have come to be. All right, so I mentioned this gravitational contraction. So as gravity accumulates, so as things get bigger, more gravity is there because of the mass, and gravity is reflecting of the mass. So as the mass gets bigger, the gravity gets bigger, and that also increases pressure, and pressure increases heat. And so that squeezing creates that intense heat center that we have in the Earth today. And other planets have that as well. Radioactivity. So remember we said radioactivity generates heat. So uranium breaking down or things like that that are radioactive, they create heat as they break down into more stable isotopes. And that creates heat. And there's heat generated today by things like that. And we actually use uranium's heat to produce energy in nuclear reactors. All right, so asteroids hitting the Earth. So anything that hits something, it creates a heat. So it heats up, and that is quite a bit of thermal energy. And so early on, we had a lot more asteroids than we do today. Today, if an asteroid hits the Earth, then it causes usually a mass extinction like the dinosaurs. But we have a lot of meteorites, and those are just simply the shooting stars. Those don't generally impact the Earth, though. They don't hit the Earth. necessarily, but they usually burn up in the atmosphere. But asteroids are larger, and asteroids can definitely hit the Earth and cause a lot of heat. All right, so cooling. So the Earth is cooling, and it's continuing to cool. Eventually, it'll be cold in the inside, and so, but it takes a long time. And so the Earth is kind of like when you take something out of the oven, and the outside cools faster, but the inside is still steamy hot. So that's how the Earth is right now. And so Mars used to be like that too, but what we find with Mars is that it's a lot smaller. It's about a third the size of the Earth. And so it has cooled much quicker, and it is now cold on the inside. So there's no more plates moving around, no more heated interior, no more magnetic field because the core is not heated. Whereas the Earth is larger, so it's taking longer to cool. All right, so that was, where we have our molten magma on the inside is from this Earth, or from the Earth cooling. So like I said, think of something taken out of the oven. So you take something out of the oven, and it's hotter on the inside, cooler, it forms a crust on the outside. So that's similar to the Earth. If it's smaller, it's going to cool faster, like the moon or Mars or Mercury. But if you look at the Earth, it's bigger. So it'd be like a bigger thing that you take out of the oven. So it takes longer to cool. All right, so the only way that we can get something called differentiation is by having it cool slowly. So heavier things are going to gravitate towards the center. So if you're cooking something, for example, soup. So all the heavier things, especially if you turn the stove off, all the heavier things are going to sink down to the bottom. And so that's what's happened with the Earth, is that the heavier things sink down towards the interior because gravity's pulling it in. And so those heavier things are nickel and core. So in our Earth's core, we have our heavier elements, which would be nickel and iron. In the core. And then the outer core, as you go out from that, it's lighter and lighter material. So the only way that happens is if it's molten to start. So that's how we know the Earth was molten, all the way molten at the beginning. And that's because we have this differentiation of different densities. So the densities are not going to be differentiated. They're not going to be leveled or changed if it's solid. So you're not going to just plow solids through other solids to get something heavier on the inside. So it has to be liquid for that to be able to change. All right, so if we look at the crust, the entire Earth, this is our material that the entire Earth is made out of. And then the Earth's crust, so notice how it's much different. So iron, if we look at the amount of iron that's on Earth, there's quite a bit, but it's almost all within the interior of the Earth. So within the core, the outer core and inner core. And then the Earth's crust, we have a lot of lighter things like oxygen and silicons or silicates. Very little iron is on the Earth's crust. So that's differentiation. So those different densities occurred because the Earth was molten throughout at the beginning. All right, so the earliest crust. So we can see this molten body here. And so basically as it was forming, so it got taken out of the oven in a sense. And so the heavier material is concentrating towards the center. Lighter material is on top. And then that lighter material starts to cool, just like when you take something out of the oven. And then eventually it forms the crust of the Earth today. None of this exists anymore. And that's because, like, if we were to look at this crust, there's lots and lots that has happened in 4 billion years. So it's been recycled, just like with the rock cycle. So we don't see rocks that are from this formation because it's simply too old. All right, so continental crust is on the top. Continental crust is much less dense. The ocean crust is more dense, like we've talked about, and that's because it's coming from the mantle, whereas the continental crust is recycled continental crust. And so it's that lighter, less dense stuff that stays on the surface.
When the Earth first forms 4.5 billion years ago, it's too hot to form with water. But the planet has water now. If it wasn't delivered by comets, then has it been here all along? To find out where the water comes from, Professor Stephen Moyges is looking for clues to when it first appears. As a geologist, he uncovers the planet's past by looking at its rocks. But the past has a big hole. It's called the Hadean, or Dark Period, because nobody knows anything about it.
The problem of the first 500 million years of Earth history for geologists has always been that you have a nightmare scenario where you don't have any rocks or minerals to investigate.
It's thought early Earth is a fireball of molten rock, but with no evidence from this time, it's just a theory. Then in 2002, Moijes makes an earth-shaking discovery: the oldest mineral sample ever found on our planet, a crystal of zircon. Locked inside these tiny grains is a vital clue. Chemical analysis of zircon crystals reveals whether they formed in the presence of water. Over 7 years, Moijes finds and dates nearly 100,000 crystals of zircon. One stands alone.
The oldest one that we've found so far is 4.38 billion years old. Now, I'd like that to sink in.
When this crystal was made, the Earth was just 180 million years old. If this line represents the age of the Earth, then the dinosaurs died out here. Rewind about 4 billion years to the end of the Dark Period. The zircon crystal was formed here.
We're talking about time spans that are beyond comprehension. So for instance, in this rock here, there are zircon crystals that are 1/3 of the age of the universe. So these things have been around for almost as long as the Earth has been a planet. Talk about time capsules.
Analysis shows this 4.4 billion year old zircon crystal forms in liquid water. Rather than a dry planet, the crystal reveals that early Earth already has water on its surface.
All right, so the crust starts to form, so that less dense material on the top starts to form, which is where we have our felsite and granite kind of rock, which is less dense than iron. And then we start to see the microcontinents forming. So we watched a video on this a while back. But that is as cooling occurs, you've got condensation, so water starts to form, and that's natural. It happens today. We can see that happening with volcanic activity today. So that and a combination of meteorites formed the water on the Earth. But the microcontinents start to form, and those microcontinents, the interior is called a craton. And so that's the original rock, basically. And so in North America, that was Laurentia. So we had watched a video on Laurentia forming. And so that was that early craton material. And so here we've got our original cratons. So you can see these are from the Archean. And so this is Laurentia. So this was called Laurentia before. So our original rock, if we look at this rock on Earth, this is our original rock. And so this was, if we date this, this is our oldest rock. So if we look at the dates of this rock compared to like this rock, we're going to see that this rock is much older. And so these are kind of the original center pieces of these continents. And so we've got shield rock, which sometimes we refer to, it's a craton that's been exposed. And so this is the Precambrian shield because this is our Precambrian era of time. So in North America, it's called the Canadian Shield. And if we go back, that is this right here. So it encompasses most of Canada. So that's why it's called the Canadian Shield. All right. And so most of it's exposed in Canada because of uplift. And so we can see here, there's parts of it in Minnesota, Wisconsin, and Michigan, which are just right below Canada. But this is our original rock that we have. And one of the videos we watched talked about volcanic rock that was in Minnesota. And so that was part of this Precambrian shield. All right, so here's some of the Precambrian shield. And so we can see in Minnesota, Wisconsin, and Michigan, you can see it kind of permeating down into here, and then same with New York. And then it makes up and encompasses a lot of Canada, so hence Canadian shield. All right, so then as the continents are growing and oceans are forming, Pangea forms. So we've got a couple continents, supercontinents before that. Then Pangea forms at the end of the Archean. And then there's more mountain building going on during the Proterozoic, and then things are breaking up and moving around. Like I mentioned before, Laurentia is our largest Proterozoic landmass, and that was most of ancient North America was made up of Laurentia. All right, so here's what a Laurentia looks like. So here's North America kind of in the center. And then just to give you some reference, Siberia, Australia, East Antarctica, Congo, Amazonian, West Africa. And so this is some mountain building that occurred. So orogeny, remember, is mountain building. And so that formed this Grenville orogeny. And then after that, there's been lots of breakup and moving around of plates, which continue today. So the plates are still moving around. So by the end of the Precambrian, about 75% of North America had formed. And that is it. So we will talk about life on Earth next time. I'll see you next time.